feel like my title gives as much justice to that intro. But yeah, the title is Rethinking Serverless with Flame. Something more inflammatory is like burning serverless to the ground, which is also my goal. But let's talk about what that means. Before I talk about that, I got to plug where I work. I work at Fly.io. They support my Phoenix development. I get to spend vast majority of my time just working directly on Phoenix, building things like Flame. Anyone a Fly.io user here? Raise your hands. Okay, awesome. A lot of people. Cool, keeping me employed. Yeah, so if you're not familiar with Fly, it's a place to deploy basically anything that runs in a Docker container, which is anything, and it's by far the best place to deploy your Elixir application. You can run a single command, have your app running a Elixir cluster across the planet. I'm currently running like a 33 node cluster on like multiple continents, and it just works. We'll see an example of that. It's not a 33 node cluster because the UI would be too messy. It's like 9 nodes, but it's still pretty cool. So definitely check us out. But we're here to talk about autoscaling and how I consider it harmful, or at least the way that developers think what autoscale means. Because the issue I've had with autoscale is like going back to, for me, the Heroku days. So if you've been around programming long enough, Heroku was like one of the first like platforms as a service where they kind of abstracted your web server. So if you've done things long enough, like I deployed my first PHP app into production in 2003. I had to call Rackspace up and like go on a sales call to like rack a server somewhere. So like we had the Rackspace days of like you call somebody and you speak to a salesperson and they charge you like an obscene amount for bandwidth, and that's how you deployed a server. And then you started having companies come up and they made it really easy to deploy a server, and they just gave you an instance somewhere. And then you had companies pop up like Heroku that said, you know what, we're going to abstract that. We're going to put a layer in between where you just give us your code and we'll run your code and you don't have to worry about the servers. So Heroku came on the scene, and the moment companies said like, well, we can take your code and we'll manage those pesky servers, then this idea of autoscaling came up, because if the companies can take your code and put it on a server, they could say, well, we'll just take your code and put it on 4 servers. So Heroku let you have this like slider in the UI, and you're like, I want to scale up. And you're just running more web servers. Like, awesome, autoscale. And you can have like, you can pay for private spaces, and they'll even do this for you instead of you having to slide things up and down. So I think autoscaling for me is like kind of, the word goes back to these days of like, we can autoscale our app because we'll just take your code and we'll run a bunch of web servers, or Heroku dynos as they were called, or Heroku workers. But like this has a serious problem. So like we have our web server here, we're running Phoenix. If we're doing background jobs, we're going to be using Oban, and let's say anything else our service is doing, like FFmpeg work, if we're doing video transcriptions, we run that together. So like the Heroku model of like, okay, these video transcriptions are super expensive, what do we do? It's like, oh, I know what to do, autoscale. Like, awesome, more web servers, we just horizontally scale. And this is like this is what's been beaten into our head of like, this is how we scale our applications. But like this has obvious problems. Like the Heroku model of like, just run more web servers, just relies on the load balancer to like split requests. And yes, this will give us more capacity because those FFmpeg jobs are really expensive. So we're using the load balancer to distribute these HTTP requests. But the problem with this is we're still putting our web requests, our APIs, our live views, our HTML pages through like the critical path of like these FFmpeg jobs. So I think a lot of us at least sense that this is not ideal, especially coming into Elixir. So we're like, okay, so where do we go from here, right? This autoscale at the web server doesn't make sense. So a lot of us will reach for like, well, Elixir is super great at vertical scale, right? We can scale horizontally when needed, but we can scale vertically much better than most folks. So I think if we get past this step, a lot of us will end up with like, okay, I have my web server, which I can scale horizontally. Maybe it's doing some standard open background job work. And then I can set up like a big beefy FFmpeg server that has a dedicated open queue, and that can churn through my CPU intensive work. And at least at this point, I'm splitting those CPU intensive, IO intensive jobs out of the critical path of my UI or my API. So I think in an ideal world, we get here architecturally, and this is a good place to be. And I'm a happy open user. At Fly, we're actually open pro users, so definitely check open out and buy the pro license. But I think this has an issue in that when we want to auto-scale horizontally, those FFmpeg servers, those big beefy servers are expensive. And we have a few options. Like either we can lean on something like Kubernetes and have that spin up like a bunch of microservices for us, or we can use a feature. Open has a dynamic scalars feature where it can like monitor a job queue and try to provision a server on different backends. Or we start just like splitting our app into microservices or AWS Lambda. So we haven't had a good answer in Elixir on like how do we go from here, which is at least more ideal than just like frantically scaling web servers, to something that can auto-scale and stay within the Elixir ecosystem. And I think like what we really want is like not auto-scale, and what I like to think about in my head is something like a cinnamon. It means the same thing, but elastic scale, right? So I think we need to get away from this term of auto-scale because it's overloaded, and think more about elastic scale and that like something that can grow and shrink back down. And not only elastic scale, but granular elastic scale. I think that's what's missing from this ideal architecture is like how do we go from this ideal architecture of like just running our Elixir code, and then how do we granularly scale these operations on our app? Because starting more web servers is just like the top level of the app. Like we're not actually scaling the things that we need to scale. We have all these operations in the app, and if we have 1,000 users on a server, running 10 servers, you can say, oh, I can run 10,000 users now. It's like, not really, right? Like the thing that we're trying to scale isn't the web traffic. I mean, if it is, sure. Like if you can run 1,000 connections on a server and you're trying to scale connections, sure, start 10 more web servers. But usually the things in our app that we're trying to scale, or the bottlenecks we hit, are these individual granular pieces. And that's what we want to think about when we think about auto scale. It's not just like scaling at the top level. It's not just like throwing everything in a background job and trying to work through jobs. It's like find the actual individual pieces in our app that are hard to scale and granularly scale those. But this is a hard problem. Because what we really want to do is like write naive code in Elixir. Like here's something that shells out to FFmpeg to generate thumbnails. Something very heavy CPU bound, IO bound. I can write it on my laptop in a few lines of code and it just works. But wouldn't it be nice if like I could do something like this and not have to like think about elastic scale or manage those pesky servers or think about my infrastructure, learn Kubernetes, split into microservices. And there's an answer to that, like, right? If we don't want to have to manage those pesky servers, like, what could we call that? Oh, we could call it serverless, right? And this is a really dumb name, but I want us to get away from it. But I think, in my mind, AWS Lambda came on the scene, branded these things as serverless to solve a real problem. And I know people deploy like entire apps into Lambda that not for elastic scale reasons, and I think that's extremely silly. But I do think it solved a real problem, and it continues to solve a real problem of granular elastic scale. Like if I had a client during my consulting days that came and said, we're using Elixir, but we want to encode videos, I'd say like, well, you don't have very many good options to stay within Elixir unless you're running a ton of orchestration code or unless you want to deploy microservices. So do that in a Lambda, right? And that bothered me. Like I didn't have a good answer to this. And like AWS's tagline for Lambda is also weird, like run code without thinking about servers or clusters. Because like Heroku is serverless by this definition, right? Like git push Heroku was serverless. I wasn't thinking about the server. Fly deploy is serverless. I'm not thinking about the server, right? It just works. Thinking about clusters, like Elixir just clusters together. So like for me, even the tagline for Lambda is silly. But the promise and the thing that solved well was compute that's elastic. You pay for only what you use. It runs this granular piece of your code, but it has all these caveats, right? But it does solve this real problem. And the issue I've seen with Lambda, among many, is like it balloons in this kind of like outrageous complexity of services. So this was shared with me, a screenshot of this was shared with me, and I thought it was fake. I was like, this is a joke. So this is a reference architecture for hosting WordPress on AWS. Right, not Lambda, but this screenshot was shared with me, and like this actually exists. That URL is real, and I fact checked it and I screenshotted this myself from that URL. But it wasn't just Lambda gives you this simple way to deploy code and run it elastically, right? It was like you buy into the AWS ecosystem and it becomes like this just labyrinth of nonsense, right? And like look, auto scaling's in the middle here somewhere. Like I don't even know what those arrows mean. I guess it's scaling EC2 instances. I'm not sure, but and this is for like a WordPress site, right? So ridiculous. But something more applicable though is another reference architecture that AWS published for video encoding. So this is something directly applicable to kinds of problems I'm trying to solve in Elixir with Elastic Scale. And this is how AWS recommends you do it, right? You don't have to think about those pesky servers or clusters, right? You just think about putting it on S3. S3 is great, actually. Object storage makes sense. But then that thing's going to trigger a Lambda. Your Lambda is going to spin up, and it calls a step function first. I've never used those. That Lambda is going to call another step function for some reason. And surprise, AWS Lambdas have a 15-minute execution time, so you can't actually encode videos there if they run for more than 15 minutes of encoding. So you have to call into another proprietary service, Elemental Media Convert. That thing runs. You pay for that. That does something with CloudWatch. It goes into another step function. It triggers Amazon SNS, which is like Phoenix PubSub, but you pay per broadcast. And then it goes into another Elemental Media package. I don't know what that does. Puts the result on S3. And surprise, like you can't get the result of this thing back in your app, so you have to put it in SQS. You actually pay for that as well. And then you go back to your app, you write the SQS consumer. That way you can say, okay, this video has thumbnails for me now. And then CloudFront's in there for probably a CDN, right? So this is awesome. Like I'm not thinking about servers, right? I'm just thinking about like proprietary services that call proprietary services that call proprietary services. So yeah, so it's just been silly, but it does solve a real problem, right? Like this does solve Elastic Compute for me. It's just I'm paying at every step of this process, right? Like the promise of Lambda was you only pay for these granular pieces and you only pay for what you use, right? It's cheap because the job comes up and Lambda runs, you pay for that compute, then it goes down. So you save money, right? You don't have to manage servers. You're just managing like 8 proprietary services now, and you're paying at every step. Like there's a middleman toll here. Like S3 you're paying for. And then to read the thing off S3, you're not paying for the egress there, but you're paying for the Lambda spin up time. You're paying for the media convert service. You're paying for the SQS insert. And these things add up. Like people are spending orders of magnitude more money on Lambda than just running something themselves. So like how can we make this better? We can use Flame. So Flame is my attempt to like just burn this serverless space to the ground. And it's not just Lambda, like Cloudflare workers. It's like Lambda, but if you could only run JavaScript and if you could only run a proprietary version of JavaScript. So it's like this whole space is extremely silly, but it does solve a real problem. But like how can we just remove the need for these services? Well, I came up with Flame. It's an acronym. Fleeting Lambda application for modular execution. There's kind of like a Phoenix theme there, right? But like this acronym is actually really important. So I burned many of my ChatGPT rate limit credits on like trying to like come up with something that encapsulated everything I wanted to convey here. So if you don't remember this acronym, that's fine because Flame is a cool name. But like there's actually a lot that we wanted to convey in this name. So fleeting is important. Like the idea of Flame is like we can run your app, right? We can run your app on an ephemeral server, short-lived, and it's your whole application, right? So what if we could treat your whole application as this idea of a Lambda, so we can co-opt the term, and just call into slices of it, right? So start your whole app, it's your whole app, you can use PubSub, you can do database inserts, right? Because it's running your whole application, but we can just modularly call into slices of your code at any time, right? So that's the Flame model. Because what we really want in a perfect world is to write our naive code, and then we come to this code and we're like, like how are we going to scale this elastically? Wouldn't it be nice if we could just like take that slice of code and scale it elastically? We could just wrap it in a Flame call. And that block of code now runs on a ephemeral server running our whole application. It's got to auto scale for us, and wouldn't that be nice? So this is what Flame does. It allows you to come in and just wrap any code in your current app. That code can do what it needs to do, like shelling out to FFmpeg, and then notice I'm doing a repo insert all. And that's fine, because again, I'm starting my whole app, right? I can start my supervision tree as normal. I probably can run a smaller database pool because I'm not serving a bunch of web users, but I can still call my repo. I can still do PubSub broadcast. And I'm using all of the primitives of the language, so it's not like this nerf runtime of a Lambda. It's our whole app with the beam. So you may have noticed, like, okay, Chris, like this code back here is kind of cheating, right? The 3 lines of naive code, it takes a video URL, And FFmpeg will accept a URL and download the file and transcode it. But I have to make that video URL public somewhere, and you could say I was cheating because AWS had to put the file on S3. So I'm skipping the fact of like AWS had to move the file close to a Lambda to pull it off and process it. So I was glossing over that fact here. And that's true. But no problem. We're running on the Beam. So we could just send the file over distributed knurling because that's how file I/O works, right? Everything's a process. So what I can do in Flame, if I need to get that file onto the server, instead of having FFmpeg download it, I can just write 2 lines of code, call file stream on the parent. That's going to open a file. That's actually a process. I can say I want to stream that file in 2K chunks, and I can do enum into on the Flame call, which is going to be another node, and it's just going to stream that file over, right? 2 lines of code, and now I have the file on the node that needs to process it. I didn't have to like put it on S3, wait for that just to read it off, right? And then delete it later, right? This is like 2 lines of code and I'm ready to go. And this is amazing, right? And this is just the Beam primitives. Like I have everything available at my fingertips. And you also may have noticed like we're closing over state here, right? There's a video struct in this interval, and that just gets closed over in the closure and run on the other node. I didn't have to think about that. The Beam just gives us that, right? So it's not like I have to rewrite my code in any way. I'm writing a Flame call, and then worst case, I maybe have to write 2 lines of code to get the file there if I have to move the file around. And you'll notice like as you're using Flame, like time and time again, like you have to change almost nothing. So like everything that we're doing in Elixir and Beam is typically process-based. So even if you have processes, live views, gen servers that we're doing some code talking to the system, and now you're like, shoot, I need to like run this somewhere else, but how do I get the results back? It turns out like you just run it somewhere else, and since processes are location transparent, you almost never have to change code. It just sends the messages back and forth. And we'll see examples of that. And the moment you do need to do something, like send a file, it's a couple lines of code, and again, we have the whole Beam at our fingertips because it's running our whole app. And if we see how this works internally, like it's super simple. So like the remarkable thing for me is like that no one's done this yet. And I think like we're the only platform that can really do this effectively. But it's like, there's very little heavy lifting that my code is doing in Flame. Like it's a remarkably small library. But what's going to happen is when you do a Flame call, we take your block of code, and there's a Fly backend built internally. Jim showed that there's a Flame Kubernetes backend. So Flame can work on any infrastructure that has a programmable API that says, please give me a server and run my code on it. So if you have a infrastructure that does that, and most of us do, Flame Kubernetes could pretty much run anywhere because you can run Kubernetes pretty much anywhere. You could actually run Kubernetes on Fly. People do that. But in any case, there's a built-in Fly backend, but the goal is wherever your app is currently running, whatever your current infrastructure is, should be able to also launch Flame. It's not Fly specific, but obviously Fly is going to be a great place to do it. But what's going to happen is when we encounter this block of code, Flame is going to say, do I have a current hot runner running this named like FFmpeg runner? If I do, I'm just going to send it this work. If I don't, I'm going to post the same API. This is the Fly API here. And I'm going to give it the Flame parent node, and in an environment variable, say, hey, here's the IP and the name to connect to. We're going to boop a server into existence. It can be a big, beefy FFmpeg server, much bigger than our web server. That's going to start a whole application, whole supervision tree. And when that thing starts up, there's a Flame process that says, like, I have this special environment variable. I'm going to connect back to my parent that you told me to connect to. And the parent's going to say, you're online, fantastic, I have work for you. And we're going to send the function over, distributed Erlang, and it's going to be run. And the amazing thing is like the amount of code this takes is like none, right? Like the Hacker News thread on a Flame blog post I wrote, like people were speculating, like I'd love to see how they did like function marshalling and encoding, like how they pulled that off. And like literally like the code on the slide here, like that's it. I'm not kidding. Like node spawn monitor, node function reference, done. Like that's the amount of code I had to write. So you take this function, it's an anonymous function, it's closing over state, right? And that video struct is going to change at runtime at any point. Distributed Erlang is like, no problem. I'm just going to send that over and run. So like I'm not thinking about the state I'm closing over, it just gets encapsulated in the function. Distributed Erlang takes care of it. Node spawn monitor function, like that's it. That's all we had to do. So that thing runs somewhere else. Good deal. Everything everything that happens in that function, like repo insert, is awesome, and then that completes, and the Flame runner is going to send the result back to the caller. That caller is blocking meanwhile, and back at the call site, we get the result of repo insert all, just like if we had called it inline on the parent node. And based on your configuration, if the FFmpeg runner has no more FFmpeg jobs, it just idles down. Just call system stop. And then your infrastructure stops it and cleans it up. And you only pay for what you use, right? You're only paying for this elastic compute. When there's no work done or no work left, it shuts down, and now you save your monies, right? So I'm stealing this quote from Jose, and when I was kind of showing him Flame and we were discussing the architecture of it, he said, this is a great example of solving a problem versus removing the problem. And I love this quote so much because like AWS, Lambda, Cloudflare Workers, like they solve a problem. They help you solve problems. Like all those proprietary services, like it's a demonstrable fact, like irrefutable. They solve a problem, right? If I want to do elastic video encoding, they help me solve that problem. They just help me solve it with like half a dozen proprietary services, right? But Flame just like removes the problem, right? Like I'm writing my code and I'm like, oh shoot, I need to elastic scale this. Flame call, and then like I'm not thinking about these elastic services. I'm not thinking about like back at the call site that was blocking, how do I get the result back? I have to put it in some message queue and pay for that. I'm not thinking about like, oh, like I need to put the result back in the database, so like I have to pay for SQS. All that goes away. I'm not thinking about the development and testing story, right? Like what if I am using this AWS Lambda pipeline? Like how do I test that locally, develop it locally? Do I run like a simulated version of AWS? Do I just connect up to AWS directly and develop against it, test against it, put my CI against it? Like if you talk to most people, like they just don't test it. In my experience, like you just test it in production, right? So it's like, no, like what if we just remove the problem? Like it's not even like, what if we like abstracted it, or what if we hid the problem? No, it's like, what if we just did none of that, right? And that's what the Beam and Flame allows us to do. Because like, this is what, 6 proprietary services? There's like 11 steps, but 6 proprietary services to solve a problem. Where Flame comes in and just says like, no, you just wrap your current code in 2 lines of code and it just goes away, right? And the only other thing you need to do is configure the Flame pool. So 2 lines of code and something in your supervision tree. And your Flame pool is just a process, right? And it sits there, you give it a named runner, and here's where I can say, like, I can configure essentially how much money I want to pay, right? I can say, like, I have these FFmpeg jobs I need to do. If I want scale to 0 behavior, I can give the pool 0 size, so like none are going to run. I can run up to some maximum, right? So if I want to just make sure I don't have unbounded growth, or I don't know if AWS gives you this feature actually. I think it's just like you can set like spinning alerts and pray. But here it's like I can, yeah, I mean literally pray. So here I can say like I never want to run more than 20 FFmpeg nodes, right? So I have this elastic pool, and then I can set a max concurrency, kind of like task casing stream. So I can at any point run 10 concurrent FFmpeg subscriptions per elastically scaled server. And if I hit that, the pool is just going to time out callers, right? And then I can tune this to my needs. I can set these things to stay hot. So idle shutdown after is like once you start up, hang out there for 30 seconds, and then if you have no work, kill yourself. It's actually, yeah, the sidebar, like talking with like, at Fly we use Elixir, but we use a lot of Go and Rust. So like talking about like supervise your children, like killing your children, like it's like, if people in Fly like hear about me talking about Beam patterns, it's always like very, very weird, very brutal, right? Like, we're like, oh no, you have that child, like you need to like brutal kill it, not just kill it anyway. Yeah. But this is all we have to think about is like, what do we want our scale to be? Do we want scale to 0 behavior? And if we don't want scale to 0 behavior, maybe we never want a cold start. We can say, I want to always have min1 running. So I could say that, I want to pay for these. I want to pay for an FFmpeg server 100% of the time because I always want one available. That way, I never have to endure a cold start. But I could also have a warm start saying I always want at application startup time it's going to block the supervision tree, provision one, and then I can even do a min idle shutdown. So like I can always cold deploy, have a pool hot and ready to service work. That way users on a cold deploy aren't going to immediately hit a cold start, and I can still shut that down if there was no work. So it gives you a lot of knobs to turn there. And this idea of a cold start is kind of like a contentious topic. On Fly, we can take your existing Elixir app and have it up and ready for work in 3 seconds. And sometimes it's like 3 to 5 seconds, but super fast, in my opinion, like outrageously fast. Like we can go from no provision server to provision server, running your whole app in 3 seconds. But the Hacker News comments will say like, my AWS Lambdas can run jobs in like milliseconds of time, right? Which is actually kind of a lie. Like if you actually look at the AWS docs, like once a Lambda is hot, it can run jobs or work really quickly, which is the same for Elixir, right? But if you actually read the fine print, AWS Lambdas have a cold start, and that cold start can vary from under 100 milliseconds to over a second, right? But AWS it's careful to say that like under production workloads, you will very infrequently hit cold starts, right? And Flame pool is the same. Like under production workloads, the pools are going to be hot, but if you're running a Flame pool, you will infrequently hit a cold start. And that cold start is going to be on the order of, a few seconds, 3 to 5 seconds, much like AWS Lambda. But there's also nuance here because the pool that I'm running is running concurrent jobs, right? Lambda is like a one-to-one process. Your FFmpeg runner is running concurrent operations, right? It's not like I'm spinning up the whole app just to run one thing. You could do that with max concurrency 1, but often you want to provision a big server and get the most out of that hardware. So it's like I'm going to spin one of these things up, and it's not like, okay, another user comes in, start another server, wait 3 seconds. It's service concurrent operations. And then if I hit my pool under high growth, I could have users incur a cold start. Because currently the pool is somewhat naive. Like we wait until the pool is at capacity to provision a new server. So there are options for us to like look at arrival rate and pre-provision. But right now you could infrequently hit cold starts. And if that happens, it's going to be a few seconds at a time and you're ready to go. And we'll see examples of cold starts actually in a demo coming up. But I'm just going to say that like AWS also has cold starts. AWS keeps your Lambdas hot, and we keep your Elixir nodes hot, and they're ready for work in milliseconds, but like even faster than that, right? Like once the node's up and running, we just send it a function to execute, and we're not even advertising, oh, we can run your workloads in milliseconds. No, it's like it just runs. Like you're not even thinking about it. It's like the speed of latency of the network, which is going to be like sub-millisecond in often cases. But we can also do other interesting things. So Lambda is stateless, and that works well for them, right? Stateless, like Lambda is like this idea of a function, like you have input, it does some work, and it produces a result. But on Beam and Elixir, like we have stateful systems. So we also have this idea of like, I have these processes in my application that might be doing expensive work. And we'll see an example of this in a moment. So in my app, I wrote that naive thumbnail code that you saw, but then I wanted to hook it up to a live view. And I wanted it to not just process a file, I wanted it to actually take a live view upload, and as the bits were coming over the wire, generate thumbnails as the file was being uploaded, which is actually a pretty interesting demo. It's like something would be very difficult to do in most languages. And Elixir makes it trivial. But I wanted to do this stateful thing, where like a live view starts up, it's sending messages of a file upload from the client into FFmpeg. FFmpeg is sending standard out back, and we're looking for the PNGs that are generated and then sending them back to a live view. So we need a process in between to manage that FFmpeg shell, receive messages, receive standard out. And that thing is a super expensive process, right? That's something that can bottleneck the system. It's doing CPU bound work. So it's something we would typically put in like a task supervisor, dynamic supervisor, like start child, right? We want to put that in our system and supervise it. It can monitor the live view, shut itself down. But how do we dynamically and elastically scale processes like that? Well, Flame has this idea of place child, right? It's like process placement. It's just like, please run this child spec, but just find somewhere to run. And run that thing with the max concurrency limits just like a Flame call. And we'll see an example of this. But in Elixir, I think we have this unique stateful systems that we build, and we also want to elastically scale those. So I think the Flame pattern is applicable to other ecosystems, but place child is something near and dear to just what we can do. All right, so let's see some actual cool stuff here. So we'll see if the demo gods are in my favor. So as long as the internet works, I think we'll be solid. with a room full of people. But the first thing I want to show off is a thumbnail generator. It's right here. Okay, so the page loaded, that's good. All right, so this is running on Fly, and it's going to take the user upload. We'll see code in a moment, but it's doing a live view upload writer, which allows you to not just put a file on a temporary file on disk, it actually allows you access to the upload chunks as they come over the wire. So we're going to take those chunks, we're going to send them to a process that runs a FFmpeg. That process is going to look for PNGs coming out of standard out and send them back to the live view to show on the page while the file is being uploaded. Nothing ever touches disk actually, which is pretty amazing. But in this case, we want to make it elastically scale, so we use flame placechild, we change one line of code, and I have this configured to scale to 0 to show a cold start, right? So I want to dispel the myth that cold starts are an issue, because that's the first thing that people on Hacker News talk about. So in this case, I could have provisioned a min1 in my pool, always have one ready, and I could have masked and hand wave this, or I could have under production workloads, users will infrequently hit a cold start. It's like, no, let's see a cold start, right? So what happens is I'm going to choose a file, and that upload writer is going to start up, it's going to hit the flame placechild, and so the progress bar is going to show, and the progress bar, between the time the progress bar shows up and the progress starts is going to be my cold start. So we can actually see what this is like as a user. So I'm going to upload a puppy video here. Okay, 2 1,000, 3 1,000, 4 1,000, 5 1,000. Whoops, oh, 6. Okay, 6 seconds. A little bit slower for a cold start, but still good, right? So that provision to server, it started my whole application. It connected back to the parent here. It started the FFmpeg process. Now that thing's up there and running, it's sending messages back to the live view. I changed no other code than one line, and it generated thumbnails for me of a puppy, which is super cute. And now that thing is actually hot and up and running, right? Actually, I think I may have set it for 10-second idle down. We'll see if we catch it. No, so it's going to do another cold start. Perfect. So we'll see how long it takes. Starting up. Oh, 0 thumbnails. So that wasn't a flame problem. That was, I think, a live view erase. We'll try again. Okay, we caught that hot. It's up and running. So it's like we can configure these things hot or not. And I'm changing one line of code. So if we go to our actual code to see this, this is the live view upload writer for this thumbnail app. It's a behavior. It lets you hook into the chunks that are coming over the wire. So you write a few lines of code and you're like, I want those chunks. So what we do on init, so when the user drops a file in the app and we start the upload, we call this function. And open is where the magic happens in this process of the app, right? When I wrote this demo, it wasn't using Flame, it was using a dynamic supervisor. So I had in my app this child spec, and I was starting this dynamic supervisor, which is essentially, it's just a gen server. Starts up, we pipe the FFmpeg, and we manage I/O into that shell. So the live view is sending chunks over. So this write chunk function is going to send a process to, or send a message to this process. That's going to send as standard input the user's chunk, and then what comes out as standard out is a bunch of messages from that shell, and that is looking for PNGs. So let's see, like I'm pattern matching on, yeah, so what comes out of standard out is like FFmpeg is, it doesn't give you, we're not writing those files to disk. It would just spam standard out with all the PNGs. So we look for a PNG preamble with binary pattern matching, and we're like, oh, we have a new PNG here, and as soon as we get the PNG preamble, we know that everything previously was the previous thumbnail. So we kind of accumulate those, and then we send a message to the caller, which is the live view process, and then the live view gets a message, and it's like, here's a PNG. It just does like a boring assign, and the thumbnail shows up on the web page. So pretty cool. But now it's like, awesome, we have this cool demo. How do we elastically scale it? So we go back to our thumbnail open, and we're like, okay, flame place child. That same child spec, and I carry on with life. And now this thing starts up on a new node and runs there, and all these process, like this gen server is running. I had to change nothing else because it's just doing message sending back to the caller, right? And that caller happens to be a live view, and that live view happens to be a process, and that process is location transparent, so like everything works, right? I'm not thinking about where things live because like the beam is made to be location transparent. Like when you hear like location transparency, it's like this really drives it home that like these things can live anywhere, and like you don't really appreciate it till like you run it somewhere else, and you're like, what? Like that just works? And you're like, oh yeah, of course. It's like it's a process. It's a message send. So there's our thumbnail generator. I didn't have to put the file on S3. I didn't have to put the file on SQS. I didn't have to like imagine how you would have written this with AWS, right? I don't know how, like you can't open a socket to a Lambda to my knowledge, so I don't even think this would be possible, right? You'd have to wait for the upload to complete, and you'd have to put it on S3, that triggers a Lambda, that Lambda then starts up, and then at that point, maybe Amazon SNS can like send a message to a browser directly, I'm not sure, but like eventually it can call back into your app. You can use Phoenix PubSub to tell a live view that it has all the thumbnails and like they would all show up at the end. But you're persisting all these things, and like what if the user is like not even actually saving the file yet, right? Like what if they haven't committed to uploading this file yet, we're still staging this information, then you have to go clean up all the stuff on S3, so it's like, no, we can just do this in line. So there's our puppy. And then another example I have is on Livebeats, which you may have seen. This is like a social music application, listen to music with your friends. It's kind of like a showcase for live view. So I can upload music here, and like it uses Phoenix Presence, but in this case I'm using NX with Bumblebee and Whisper. And here's where like a cold start really matters. So I want to show you a very cold start. So we'll talk about ML workloads in a bit, but I think Flame could work really well for elastic ML workloads. But we have to really consider cold starts in this case, because there's a lot of time spent often just moving these large models around. Like you just have to get them on to the machine that starts. They can be like tens of gigabytes. And then loading those models, compiling them, loading them into memory can take like tens of seconds. So in this case, usually it's about 30 seconds for me to load up Whisper with Bumblebee. So I'm going to upload a song. We'll see how it works on conference Wi-Fi. This is actually like solid. Okay. Yeah, as the upload's being uploaded here, live view is actually like parsing this MP3. So you notice the artist just came out, the attribution showed up. Pretty cool, didn't have to touch disk there. And now when I hit save, I'm going to, in the naive approach, I was just running a async task after I inserted the video to call into Bumblebee and send messages back to the live view. But to change that from something that didn't scale to something that elastically scaled, again, we'll see how I change one line. So when I save this, it's actually going to spin up a Flame, and it's going to run that Bumblebee code. Maybe, there we go, okay. So this, oh, we got some users here, cool. So this is going to take like 30 seconds here. We'll see. I like this song too. So we'll see, what, 15 seconds now. So this is like actually a true cold start. And this is like ML workloads, like you have to, if you ever deployed anything ML-wise, like you'll understand, like you have to plan for, you can't just like spin these things up and run something instantly. So we're waiting, that thing is compiling the model right now, loading it. We hit 30 seconds, okay, and now we're getting transcriptions, right? And it's working. That's running in a Flame. So if I delete this file now, I'll be able to catch this thing hot. And again, I could have said like min1 and always had one running, right? So it's like not like you always would pay that. I just want to demonstrate like if you want scale to zero behavior, you have to consider cold starts, right? And for a lot of workloads like that thumbnail generator, 3 seconds waiting on a upload that's going to take a minute or 10 minutes doesn't matter, right? But something that's going to take 30 seconds to upload does matter. So if we catch this thing hot now, that runners hasn't idled itself down yet, and we'll see how fast it takes to get transcriptions. Was I drawn into your orbit, or were you drawn into mine? Okay, so it should be actually like faster than real time of the song at this point, because that thing was running NX and Bumblebee and just ready to go, and it's hot. So if you were deploying this into production, you would probably have not min0, or you would have a warm one start up, and then maybe if your app didn't have real users, you could scale it down to 0. But again, cold starts for ML workloads are going to be highly considered. Yeah, Presence is working. Actually, I haven't used Livebeats with other people in like a year, so this is actually fun. Like, your code works. Like, look at this. It's cool. Yeah, so that's running NX and Bumblebee. So let's see an example of what that code looks like. Okay, so let's go into Livebeats. So we can see I'm configuring my Flame backend here with a different different CPU and memory. So these things can run. It's not like just like running your same web server. You can spin up beefy hardware. But let's go see what I'm doing here. I think it's in the media library. So when the file is inserted, after we actually consume the file, we're going to call this async transcribe. And the way I wrote this initially was just task supervisor start child, right? And now you're like, shoot, like, this is the first time I actually played with Bumblebee when I wrote this, and it was like, this is amazing, like machine learning and Elixir. But then it's like, okay, how do we scale this? Because if we go into our audio module, like this is doing expensive work, right? We're calling into FFmpeg, which is kind of like the unsung hero of this talk. But right, we're shelling out to FFmpeg. That's going to do conversion of the audio file to wave format, specifically to what the model is expecting. And then we call NX serving, batch run, and this is like two like heavily CPU intensive operations, right? Like, or GPU, depending on what we're running, right? So like we need to scale this. Like, what do we do? Like this is difficult, right? And when this thing is done running, like it sends messages back to the live view. So like how would we put this on Lambda? I guess we could pay for a proprietary API, and that could be one way to get around it. But it's like, no, I just want to run this myself, right? Well, what we can do is we can, instead of task supervisor start child, I do a flame cast. Flame cast is like flame call, except it's async. And that thing is going to call my FFmpeg stuff. Look, it's doing a pub/sub broadcast. Like, oh shoot, okay, this is where I need to hook into an external service. No, like this is running your whole app, right? Like the A in flame has specific meaning, right? I'm doing my pub/sub broadcast, and that just works because it's running distributed Erlang. It's running your whole app. You can start your pub/sub process in your supervision tree, right? Oh, it's doing a repo update all. Like, no problem. You can do database inserts inside Flames. It's running your whole app, right? But we're only running this slice of code here, and we're running that elastically. So I changed one line of code, and now this thing is running, and it's still doing work. It's still sending and streaming those results back to the live view, which is on another node. I don't care about that. I didn't have to change any of my app to consider the fact that this is running somewhere else. Again, messages just arrive, and we do like assign, or in this case I'm using streams. Stream, a couple lines of code. Now the UI is getting real-time updates, but it's getting real-time updates from a node dynamically provisioned somewhere else on our infrastructure. The messages just arrive. Like seriously, like it's ridiculous. I don't understand how the Beam works and how we've had like these kind of features for so long. And there's another, people are still on this. That's fun. There's another demo I want to show, which is a world page speed application. I haven't tweeted about this. It's the first time you're seeing this. So this is another example I put together. Like, you know, like Google has their page speed test where you can see how fast your page loads, and you get the score. You get a score. But often, like most of us, like we're deployed in like US East 1, and like our website's super fast if we live in the US, right? But then it's slow elsewhere. Or we have a CDN to deal with the slowness of our assets. But like, you know, like what does your page speed like look like as seen from users around the planet? So I wrote an app to do that. Like it's like ridiculously simple, but let's see what it looks like. And again, I have scale to zero behavior here, just to show that like I said, I'm not masking cold start. So what we see is when I hit go here, it's going to start headless Chrome, which is expensive, right? Something that's going to be hard to elastically scale, uses a lot of memory. We're loading a website. It's going to boot headless Chrome. It's going to load the web page, because to know the page speed, you actually have to run a web browser. You need to download the JavaScript. You need to evaluate it, and you need to download all the images. And we're essentially waiting for the window load event to report back the actual page load time as seen from users around the world. So we need to run a flame in different continents around the world, running headless Chrome, and update the live view of that result. So when I hit go here, you will see all the statuses of the metrics will say starting browser, and the starting browser is actually the cold start time. And then when it goes from starting browser to loading page is when it's actually started the app and it's running your code. So let's see, let's load Hacker News here. Okay, apparently autocomplete didn't work. Okay. Oh, who was on this? Get off this. Okay, so you ruined my demo. No, I really wanted to show cold starts there, so now we have to wait 30 seconds. Okay, so we hit this hot because we had active users, right? This app is like, I'm gonna make so much money, I have users. Okay, so yeah, this is still calling those flames that were started up around the world. Stop using the app because I do want to show a cold start. I guess I can just like do an app restart. But this is actually, hold on, I'm gonna try it again now. The problem is every time I hit these runners, then they're gonna bump their timeouts. And if we load world page speed, if we load this app, I can just like brag about how fast this app is. So this app is running in all the regions that I'm running the headless Chrome in, so it's gonna be super fast. So I'm going to wait a few seconds here, as long as people aren't running this in the background. Stop. Oh, okay, so no. But the cool thing is, okay, so let's see how fast, like world page speed itself, so like in Illinois, right? US is actually like one of the slower ones on here, 160 milliseconds. And if you look at like Tokyo, Japan, 58 milliseconds, amazing. So we're running an Elixir node for this live view web app in all of the countries that you see here. And that's why it's fast in all those regions, right? Because we didn't have to like go across the ocean to load the web page. So 58 milliseconds in Tokyo because we have an Elixir node running in Tokyo. They're all clustered together. So I'll come back to this and we'll try after we see the code to show a cold start. No, people are still using it. Stop. All right, so let's see the code for this. I mean, it would have just said starting browser, but it was just cool to see like 5 seconds later what it did. So what that's doing in Flame is like it's booting your whole application, it's starting headless Chrome, Chrome runs, it's sending a message back to the live view at each step of the process, telling you like, okay, we're starting the web page. As the results come in, it's sending a message. So if I load that live view up, what we're doing in this live view when you hit handle event go is we do a start async, just an async process. And like, again, this is like, you have the whole beam. Like this is just, this whole demo, like this writing, like seriously, like I've been doing this for 10 years. And like every time I write anything interesting with Beam, you're just like, it defies reason on how ridiculous it is. But let's see this, right? Like, so what I wanted to do in this example is like, I have to run a browser in all those places to know how fast those web pages are. So any live view that you land on, wherever you are in the world, I need to like go do all those browser timing things. So what I do is I get a bunch of nodes, like members list is using Phoenix Tracker internally, but I'm basically just saying, give me all the nodes on the cluster. And then I start async in live view, and I'm just using ERPC multi-call. It's just built into Erlang. It's just doing an RPC call. You give it a list of nodes, and it's going to run the function on all those nodes. It's going to block till they all return a result. And within that function, in live view, I'm sending the parent PID back, right? Because our parent live view process is going to be needing to get these results back from all these other nodes that were discovered on the cluster, right? Multi-call calls this function runs on another node. So if I hop into time nav before Flame, I just had this code here. I have this browser module, it has a time navigation function, it just runs headless Chrome underneath, and it gets a result back of timing, and that timing just has a bunch of performance metrics. When it gets the result, it sends the parent a message, which that parent is a live view PID, and we're like, either we're complete, here's the metrics, or there was an error. And this is happening on another node, right? We did an ERPC multi-call. It happened on another node. The fact that it happened on another node doesn't matter because the parent's a process, and processes are location transparent, so it makes it to the live view back in the country where you started, and it just updates. So you're like, wow, this is awesome, ERPC multi-call, but you're like, how would we elastically scale this, right? We can't be running headless Chrome for every user that visits our web app, right? Like all of our UIs, all of our live views, like we want to keep that expensive thing out of the critical path of our app. Well, I just wrap this thing that's running already on another node in a Flame call, which is going to put it on another ephemeral node. We're going to close over the parent here, right? And that parent's a process, so like we're already running on another node, and now we're like, no, I want you on another node. And the parent gets closed over, that's just a process, it's location transparent, it doesn't matter. When that Flame does its work, it sends the parent a message, and we didn't have to go back to the multi-call node, we just go back directly to the live view process. And we have to change no other code. So what I'm trying to say is I wrap it in a Flame call and like it just worked, but it's like a Flame call within a multi-call, and it's ridiculous. And let's see if we can get a cold start now. No one load this. Don't do it. Starting browser, awesome. So what's happening here? Like we're provisioning a machine, we're running your whole app there, we're starting the app, loading page, loading page, loading page. It booted headless Chrome, it's running the web page, we're sending messages back as this is happening, and this just did this across the world. Like what? Like really? Like, yeah, so this is what Flame enables for us, right? And this cold start example was, like I said, 3 to 5 seconds, and that's 3 to 5 seconds to boot your whole app with Chrome inside of it. Like Chrome is not like, you know, it's like, if we're familiar with Slack, like hundreds of megabytes, right? So like this Docker image of my app has Chrome, headless Chrome included, and like no problem. We'll just boot it up and run it there, right? Like just ridiculous. Seriously, like in the idea of like distributed Erlang not working on like internet scale, like So I've done this enough times that like, no, it just works. Like, no problem. Like if the fiber was cut between us and Sao Paulo, like that wouldn't show up, but the rest of the app would continue to work. So again, Flame lets you just wrap things and not think about it, and there's all kinds of interesting things you can do. And not pay AWS for that, right? I wasn't thinking about, like, imagine how you'd have done this with AWS. Again, how would I have gotten the results back to the UI in real time? Probably would have paid several proprietary services, and it would have been much slower. But the goal of Flame is like to be unremarkable, which is funny. Like Flame is almost like, it's remarkable in how unremarkable it is. So like you change a couple lines of code. So like when people like have tweeted like their Flame code, you're like even for me, you're like, what? Like, you know, you're excited to see it, but you're like, oh, like to show off your Flame examples is like a Flame call. You're like, oh, okay. Like it's so like, you're like, that's it? Like, okay, I guess that's it. But that's the goal. Like elastic scale should be a boring decision on Beam, right? With Flame, we can say like, it should be as boring as do I want concurrency, right? So when you're in your code and you're like writing some code and you're like, oh, this thing could be run concurrently. What do? You reach for task. Like it should be as a boring decision as that, right? If I want concurrency, I'm gonna reach for task. And I'm thinking like, okay, I actually wanna make sure this thing works. I want durability. I reach for open. And now you have a third boring question to ask yourself. Oh, does this need elastic scale? Okay, wrap it in a Flame call. And it should be no different than this decision process of a task, right? And then you just carry on with life shipping features. Like it should be boring. And it is boring because you're changing almost no code to do it. And you can combine these aspects, right? Like sometimes we want concurrency, sometimes we want durability, sometimes we want elastic scale, right? But oftentimes you might say like, well, I want to make sure those thumbnails are generated, right? A user uploaded a file. If that fails for whatever reason, I want to retry it. So you combine that with open, right? So you're decoupling your durability from your elastic scale. So we can have an open job fire up, and it's like, okay, I need to encode this video. If this fails, it's going to be retried. And open has features to dynamically scale your app, and they also allow you to hook into, you can manually call and hook into pool growth, right? So the only missing piece here is you would need to have open reach into our pool growth callbacks. So as Flame is dynamically scaling up and down, open queue concurrency is going to also want to scale dynamically up and down to either send more jobs when you have more capacity or reduce jobs. But you can get both cases here, what you want. I want durability and I want elastic scale. Or if I'm running headless Chrome in real time to get performance reports, I don't need to put that in my Postgres database to be pulled off in a job to run because I just want to report back to the UI, was I able to access that website, right? If I was not, then I just report to the UI error, right? So sometimes you want durability, sometimes you don't. And you're going to reach for the same tools, like I said, just like task or open insert or Flame call. You can combine them or you can use them separately. It depends on the guarantees that you want. And I think like a missing part of this model is edge computing. And I think edge computing is like also an overloaded term. And like somehow edge computing has turned into like running JavaScript on the edge. I don't know why, honestly, but like it's weird. Yeah, this is a whole nother talk, but like it's weird to me that like running on the edge, like Cloudflare things or Lambda at the edge, like AWS has a service for running on the edge and you can only run Lambdas there, which is weird. Why not just let you run anything? But it's weird because like if you can already run all these things at the edge, like the idea is like, well, I can run close to the user so my JavaScript single page app can like talk to my JavaScript on the server. So it's like, well, if you're already running on the edge, why not you just run your whole UI on the edge and you're close to the user? But anyway, that's another talk. But the edge is, like I'm not trying to discount it. Like it makes sense to run close to a user. And I think all of us like intuitively understand like the CDN model, like intuitively makes sense, right? Like, and it makes sense because like the speed of light is a thing. So like running close to the user is a necessity because the speed of light is a reality. So when I want to serve my assets close to a user, like my JavaScripts or my style sheets or my images, I put those things on a CDN at the edge close to each user, so that way web pages load faster and they're not waiting for the speed of light. And I think all of us understand this, right? But the same thing applies to elastic compute, and I think not all of us think about that, right? So the idea is like when I'm running these flames, like it's even more important than like the CDN idea, right? If I have a user upload a file in Europe, and I spin up a Lambda in the US, right? Like I have to get that over there, right? So do I put it on S3, right? And then that's gonna take time to hop over the ocean. I'm paying egress fees potentially. If I have a server running in Europe and then I need to put it on my bucket, which is located in US East 1, that's a huge egress fee, right? Like this matters from both speed of light standpoint and costs. So what you really want is you wanna take the CDN idea, you wanna run your server there on the edge, and then you wanna put the requester of resources as close as possible to the client, right? So in the end user state, they're requesting some JavaScript. You want to put that JavaScript as close as possible to them. When a Elixir application says, I want elastic compute, you want to put that elastic compute as close as possible to the Elixir node that asked for it, right? So just like in our web page speed example, if I had my server in Tokyo say like, oh shoot, I want to do this elastically, let's start a Lambda, and the Lambda in US East 1 was like, I got you fam, like that would not be doing what we want it to do, right? You have to run the compute in Tokyo to have that make sense, but what you really want is sending messages back and forth. You want it to be as fast as possible, sending data back and forth like that file stream, right? Like this line here makes a big difference if I'm in Europe calling into a node in US East 1, right? What I really want is when I ask for a Flame call that the node is provisioned as close as possible to the parent. And on fly, that'd be best case scenario, the same physical rack server as the node that your app's running on. So if you ask for a new fly machine, it will know that if it knows it's running a Docker image cached locally, it will pick the host by default. So like if there's capacity on the server that's running your current app and you're requesting a machine of the same capacity, like CPU and memory, it will just run it there. So like you're literally running on the same rack server, best case, and worst case, you're running in the same region with essentially the same data center, right? So by default, like it's just gonna do what you want, right? Like, this is the whole thing of like solving a problem versus removing the problem. Like when you ask for compute, it's gonna run the compute as close as possible to the Elixir node that asked for it. That's just how it works. That's just how it should work. So if you're using Kubernetes or whatever, ideally you have a similar setup. And again, because like this matters, right? The message sending between nodes matters. Speed of light's a thing, especially when you start moving assets around. And we've seen some use cases. So I think like anything that is heavy IO CPU file media bound, like is obvious. Like FFmpeg, like I said, is like the unsung hero here. We saw Chrome driver, which I think is super interesting. Like I kind of want to make like my own AI agent that just like unleash it on the internet, like, you know, go crawl around and do stuff. But I think like if you were building, like in all seriousness, like a Google bot today, like you would use Flame to do that, right? Like you would start up headless Chrome, drive it from Elixir, go crawl the internet and do it like you're building a search index, you're doing AI, doing whatever you need. That would be super cool, and you could reach for Flame for that. The boring business decision that I think most of us have done is like we need to do PDF generation, so this would be perfect for that. Like as a consultant, like you know, users are asked for like, I want to be emailed a PDF monthly of my sales report, and you're like, how do we generate a PDF? Like we could reach for a PDF library and like hand build the PDF, or we could just do, you know, how do we make that look nice? So we're like, oh, browser, it's easy to code a web page and make that look nice. Wouldn't it be nice just to like take a web page, convert it to a PDF? So at least in the past, I've done this like a dozen times where you have a web page that renders the that has the PDF document just rendered with HTML, CSS. You ask the browser to convert that to PDF for you, and then you email that to the user. So this would be a perfect example for that. You write it naively, use headless Chrome, and wrap it in a Flame call, and now it scales. And then data pipeline ETL is another thing where you have these like spiked, bursty workloads come in, and you need to do a bunch of work on some data, and then go away. And then ML here, I think it's actually a really interesting use case for Flame, but we kind of saw that like cold starts really matter. If you've done any serious work with these big models, like I think folks will intuitively know this, but like just getting these things started and running is just like work. Like you're moving like tens of gigabytes around just to like get the machine running. So it's like just to even start, you need to get the model there, and that's got to be sent over the network. Once it's there, you have to load it. So you're talking like tens of seconds at a time. So I think this is really interesting, but you have to consider cold starts. So most likely you're not doing scale to zero behavior if you're deploying ML today in production, unless you don't care about a 30-second latency, and maybe your background job doesn't mind that. But what you're really gonna do if you're actually deploying a model for real is you're probably gonna want to just run the minimum amount possible, keep one hot, and you could still dynamically, elastically scale as needed. using Flame. And then again, you can run different kinds of hardware of your same application, right? So it's taking your current Docker image here, and then on fly I could say, I actually want to run this with a NVIDIA A100. So I'm running my app on GPU as needed in Flame, and then my regular app is just running on, the plebe CPU, whatever I need. So this is a super interesting aspect, but again, you have to really consider cold deploys. You're going to want a minimum of 1 probably, and then your idle shutdown is probably like you're spending so much time starting these things and just getting them running on the GPU, you don't want to throw them away, right? So your idle shutdown is likely going to be longer, and you're probably running a pool of these at all times and just handling the bursty workloads as they come in. That's all I have. So definitely check it out. I want to hear what folks are building with Flame. The backends, like I said, we have a Flame Kubernetes backend. Jim published a package maybe for, okay, so Jim wants to do a GCP backend not using Kubernetes that just does, just hits the API directly. So like literally the Fly backend is like 150 lines of code. The Fly Kubernetes backend is less than 200 lines of code. So like Flame can work on pretty much any infrastructure. So if you're interested in having it work on whatever infrastructure you have that's not using Kubernetes or Fly, come talk to me, because like literally the code is like you add rec to your project and you do like a rec post, and like it's an absurdly small amount of code because the Beam just does everything. So yeah, that's all I have. Thanks a lot. Questions? No questions?
Hello? There we go. Okay. We had 2 questions here I think that are probably worth answering, and then we got a break. Are Flame calls testable? What's the testing approach if Flame is
Perfect.
used?
I was supposed to mention this. I thought I did, but so yeah, one of the key things of like Lambda, I mentioned testing, I didn't directly address it though. Yeah, how do you test this, right? Like one of the solving a problem versus remove them problem is like you just test it, right? So the Flame backend for dev and test by default is the Flame local backend. And guess what the Flame local backend does? It just runs your function. So it's like we have a runtime locally. We have a compute resource already running our app. We just run your code. So the story is like the code that you were testing, writing it naively when you wrap it in a Flame call, it just runs on your laptop and you just run your tests. So yeah, testing is just write your tests like you normally would, and you don't have to worry about those pesky servers. So yeah, that's the answer.
And the next question is, how do you recover from a crash in the Flame process?
Yeah, you don't. I mean, you recover in the same way that you would from, like if I had that thing in a task and you ask how would I recover from a crash in that task? And it's like, well, are you monitoring that task? Are you going to restart it? Yeah, this is a long answer, but like in the same way you would handle a crash in any other process you started, right? If you don't want that thing to crash, you could trap exits. That's very rarely what you want to do, but it makes no difference here, right? It's just like where that code is running is really the only difference. But like you could remotely monitor whatever's running inside the Flame, and if that thing went down, it's going to be the same strategy of however you would handle the failure wherever you're running it. So that's the answer.
All right, thank you very much. Let's give him a big hand.